In 1993, a secretive Formula One supplier began work on fighter jets and race cars, never bicycles. 14 years later, they stunned the cycling world with a 25,000-pound bike loaded with data sensors, years ahead of anything else on the road. How did racing's most demanding engineering leap from the paddock to the peloton, and what did it cost to break every rule? This is where Factor's true story begins. BF1 Systems opened its doors in Norfolk in 1993, staffed by engineers whose daily work revolved around the world's most demanding machines. Formula One teams relied on their expertise for steering wheels packed with electronics, carbon fiber parts that could withstand the violence of a crash, and sensor systems designed to capture data at racing speeds. Their client list stretched beyond the paddock. Classified aerospace projects and defense contracts called for the same obsession with precision and secrecy. A team of about 30 engineers worked in a lab where autoclaves hummed and the smell of resin hung in the air. Every component was measured, simulated, and tested to tolerances that left no room for error. In Formula One, a miscalculation could cost a championship. In aerospace, the stakes were even higher. The culture inside BF1 was defined by a belief that anything could be engineered if you understood the forces at play. Data acquisition was not a buzzword, it was the backbone of every project. Whether it was a steering wheel with a dozen sensors or a composite structure for a fighter jet, the goal was always the same: make it lighter, stronger, and smarter than the competition. Yet for all their technical mastery, bicycles were a world apart. No one at BF1 had ever built one. The cycling industry, from their vantage, seemed almost quaint, dominated by tradition, slow to adopt the integration and simulation that Formula One took for granted. That would change when John Bailey, the company's managing director, proposed a radical idea: use everything they knew about speed, composites, and electronics to build a bicycle unlike anything before. Not as a commercial product, but as a showcase, a proof of what Formula One engineering could do when let loose on the open road. The Factor 001 was never meant for mass production. It was a statement, a 25,000-pound experiment that asked what cycling could become if Formula One thinking was applied without compromise. When the prototype was revealed in 2007, it looked and felt like nothing else on the road. At its core, the 001 was built around a full suite of sensors and electronics: power, speed, heart rate, even skin temperature and breathing rate. Every metric was tracked to medical standards, not just for curiosity, but to give riders the kind of data Formula One engineers rely on to win races. The electronics were not bolted on as an afterthought. They were built into the frame, with wiring routed inside the carbon monocoque and a custom head unit mounted at the cockpit. There was no off-the-shelf solution that could handle the data stream the 001 produced, so the team designed their own from scratch. Simon Roberts, the project lead, remembers the skepticism. People said it was overkill. They had seen the errors in standard power meters, and if you were coming from Formula One, that was unacceptable. The 001 cranks used strain gauges that measured force with a margin of error below 0.1%. Even the hydraulic disc brakes, paired with integrated Shimano Di2 shifting, were a world first for a road bike. Every element was hidden, every surface as clean as possible. The result was a machine that blurred the line between racing bike and scientific instrument. The price tag, more than double most super bikes at the time, was a shock. But for the engineers involved, the real cost was in the process, proving that ideas from the world's fastest cars could actually survive the real world of cycling. The Factor 001 was not just a prototype, it was a challenge to the entire industry and a seed for a new way of thinking about bicycle design. Inside the BF1 workshop, the process of building the Factor 001 started long before a single fiber was cut. Engineers gathered around computer screens, running simulation after simulation to predict how every load and vibration would travel through the frame. The lessons learned from Formula One were everywhere. Nothing left to chance, every variable controlled. Carbon sheets were selected for their precise modulus, then stacked by hand in a layup sequence that followed strict patterns set by finite element analysis. Each layer's orientation and resin content were measured with the same rigor as a race car monocoque. Even the resin ratio, often left to experience in traditional cycling factories, was dialed in using custom jigs, ensuring that the frame's final weight and stiffness matched the digital model, not just the engineer's hopes. Once the layup was complete, the frame entered an autoclave, an industrial pressure oven more common in aerospace than in bike workshops. Here, heat and pressure fused the carbon into a single monocoque shell, eliminating air pockets and bonding the layers with microscopic consistency. And technicians monitored every stage, using sensors and quality control jigs to check for deviations as small as 1/10 of a millimeter. If a frame failed to meet tolerance, it was rejected without hesitation. The expectation was total repeatability. And in Formula One, a single out-of-spec component could end a race before it began. That same zero-compromise mindset guided every step, from the first resin infusion to the final curing cycle. This approach allowed the team to scale their methods beyond a one-off prototype. The process was not just about making one perfect frame, it was about proving that perfection could be repeated again and again with the same precision that defined their F1 work. The backbone of Factor's production was not just carbon fiber or clever design, it was a manufacturing discipline that measured success in microns, not just in grams or watts. Layup decisions at Factor began with a simple question: what does the rider need to feel on the road? Engineers studied how unidirectional carbon fibers could be layered at precise angles, each orientation influencing how the frame flexed or resisted force. For a sprinter, fibers aligned along the down tube and chainstays delivered maximum stiffness, translating every watt into forward motion with barely a hint of flex. But that same stiffness, if carried too far, turned rough roads into a punishing ride and robbed a climber of comfort and control. A trade-off emerged: lay fibers for pure power and the bike sprints like a missile but jars the rider over broken tarmac. Shift the angles to favor vertical compliance and the frame absorbs vibrations, letting a climber stay fresh on long ascents, but at the expense of some snap in the final meters of a sprint. Engineers visualize this balance as a slider push one way for sprint stiffness, push the other for climbing comfort. Every layup sequence was a negotiation, modulus, angle, and resin content mapped to a matrix of stiffness versus compliance. Testing went beyond the lab. Factor's team built prototypes with different fiber orientations and handed them to riders who could pinpoint differences in acceleration, cornering, or fatigue after hours in the saddle. A frame tuned for stiffness might win the drag race out of a corner, but leave hands tingling after a cobbled descent. The real challenge was finding the sweet spot, where the numbers from finite element models match the sensations reported on the road. In this way, every technical choice became a lived experience, with the trade-off slider guiding each new generation of frames. Israel Premier Tech rolled their new bikes out for the first time at a World Tour training camp, mechanics quietly checking every cable and bolt before the riders clipped in. The partnership put Factor's designs to the test in a way no lab ever could. Stage races meant relentless punishment, rain, dust, neutral service wheel swaps, and the kind of feedback only a pro mechanic or sprinter can give. In one early race block, a mechanic flagged a minor flex at the cockpit under heavy sprint loads. Within days, engineers back at Factor's workshop were running simulations and sending revised cockpit parts for the team to try. Riders noticed the difference immediately. One commented that the front end just feels sharper now, especially when you're fighting for position. The cycle of feedback, redesign, and retests became routine. For Factor, every race was another data point, every rider's complaint a chance to refine the details that separate a good bike from a winning one. OSTRO VAM and O2 VAM stand as proof that Factor's Formula One philosophy has become more than an experiment. The OSTRO VAM, shaped for pure aerodynamic efficiency, slices through the wind with deep tube profiles and an integrated cockpit, chasing every marginal gain in the tunnel. Factor claims it is the fastest UCI legal road bike, and its design is validated not just by lab numbers but by race results. The O2 VAM, built for the mountains, strips weight to the minimum with high modulus carbon, and pared down shapes engineered for the steepest climbs, yet still stiff under power. On the track, the Hanzo platform delivered a world record 3 minutes, 40.730 seconds in team pursuit at Paris, a time that stands as objective proof of Factor's engineering. These bikes are not just concepts. They are the outcome of relentless testing, measurable data, and victories at the highest level. Right now, Formula One derived technology defines the sharpest edge of professional cycling. As racing speeds climb and data drives every pedal stroke, engineering breakthroughs shape who wins and how we ride. The real race is not just on the road, it is in the labs behind every carbon fiber frame. What's next?